All right, cool. I think today we're just wrapping up homework number 2. We have like two different setups for 4-bar linkages, and we're trying to solve for like how fast everything is moving at a given point in time. So I just wanted to like run through kind of the process that we've used so far and stop for questions along the way or see like what's going on. Just check in. So we created this like set of equations. Oh. What am I doing? There we go. So we created like a set of equations that describe constraints on position. And there's a nice question about like when does this have to be true? And it has to be true all the time. Like if these hinges are connecting these parts, this is always true. Like I have to be able to go from O to A and A to B. I have to end up at B the same way as going like O to C and C to B. So even as this thing is moving, no matter how fast it's moving, that has to be true, which meant that the speeds also have to follow that equation, like the velocities of everything. But that velocity of C is 0, so now I just have a constraint on those relative velocities of like O to A, B to A, and then B to C. So constraints on like how fast stuff is moving relative to one another. So if this is like A and this is B, we would have like, first we solve A, figure out what the angles are, and then I can plug those into B. But we already knew like where A, B, and C are, like where those actual locations are. So really all we needed was the sine and cosine components of them. Ooh. And I think this is where we were kind of working on Friday, was figuring out what is cosine, what are those sine and cosine components of where those vectors are, of those relative vectors. And here, I think we were working. I think we were plugging all of these in, but like because all those angles are describing like relative positions, it's always like L1, 2, and 3 as our hypotenuse kind of parts there. So then theta 1 was like the I and j components of A. Theta 2 was that B minus A, so relative position of B to A. So 0.5 minus, so 0.5 plus 0.2. And then sine was the relative B to A again, so 0.86 minus 0.15. And then theta 3 was B to C, so we had cosine of like 0.5 minus 1, and then 0.86 minus 0. Speed run through the process of where we ended up last time. Then I think we ended up like plugging into like a system of equations, right? Is it in here? Yeah, like I set up, here's two equations, and then tell fsolve, which is like function solver. Like if I have a function, it'll figure out when it's equal to 0. So we got 1 and 2.56. At least those were the numbers that I got. How about you? What numbers did you get? Similar? Different? There should be some difference, right? At some point, should be rounding error somewhere in there.
You said 1 and 2.56?
That's what I got, yeah. How does that sound?
Yep.
What does that mean for like what this thing is doing? Like when we look at this device, like this 4-bar linkage, what's happening to link 2? Is it moving this way, like down, or is it moving up? So we figured out, we know theta 1 dot is 10 radian per second for all time. So theta 1 is always rotating about 1 revolution per second. Like what was that? 2.6? 2.6. So which way is link 2? Is it moving up? Is it moving down? Fast? Slow? What do we think? What's it doing? Yeah. Yeah, it's hard to tell.
This direction.
Okay.
Or one is.
Yeah.
So we know it is. So theta 2 should be like
Decreasing 1 radian per second.
theta 2. That would be probably like that. It's probably increasing a little bit.
I mean, my first thought was that it was decreasing, but I've seen it not moving as far.
I know, yeah,
It was like how it interacts together.
Okay. What is it doing? All right, yeah, good math.
We probably all have to just like starting off with
Yeah.
the beginning, and then eventually, because at that point, if beta 3 keeps moving downwards, then beta 2 is going to be moving. It's going to be like this. So beta 2 is actually in a negative direction.
Yeah, yeah. Yeah, like, but at this point in time, everything's positive, so everything's opening.
So when it says for all, so beta 1 is for all times.
Yeah. Yeah, the other ones keep changing, right? It's like if we think about theta 3, it's gotta go left, then right, then left.
We've done like all the sine function, cosine function.
Not quite, because we have like sines and cosines have to add up to a constant value. So it ends up being like it kind of oscillates. Like it's definitely an oscillating function. It's a combination of it. Yeah, not quite like a sine wave. Yeah. All right, so good like math check here is like we called 10 radians per second positive, right? So the angle is opening. So the only way that they would be closing is if it's a negative theta dot. That's like kind of if we want to math our way through it of like positive open, negative close. Doors open, close. Because we always define like, at least in this case, you can define theta wherever you want. Like there's got to be a 0 for theta. I like x-axis just because then cosine theta is always describing horizontal. I don't have to like rederive it in my head. So everything is kind of opening in this case, like theta 2 dot slowly moving up, and theta 3 dot is coming this way. No? Some squinting with like, I don't believe it. Zero, one, oh, cool. Let's go maybe 20. Yeah, we're something like this, right? Like So if we're thinking about like -0.2, +0.15, 1/4, and then we have a 1 meter up and a 1 meter over for those other two links. A is moving around in a circle because that's our crank arm. Link 2 is following, like the center of link 2 follows this kind of weird egg loop. And then link 3 is our rocker arm, where it goes to some max value, stops, and then starts moving back the other way. And it's not quite like a sine wave. It definitely oscillates and it repeats, but it's not like a sine. Like we're not moving in a perfect circle, right? We could design a 4-bar linkage that moves in a circle. Now we've got like sine wave that way. And here, kind of going from, if we look at how fast theta 1 dot is always 10 radians per second, theta 2 and theta 3, kind of, yeah, these like other shapes there. And we're somewhere,
Where was it?
so pi, I always forget. I gotta switch this over to switch it to degrees. So we're somewhere like over here, right? So theta 2 dot is like 1 radian per second, and then theta 3 dot is over here. And as we keep moving, at some point, theta 2 becomes negative, like it's moving backwards. Same thing with theta 3 dot. Cool, kind of cool. And then vector, so the question in chat is like these vectors. So let's try this, because we had, so we're done, like, at least if we plug that in, solve for those values, we're kind of like done with that. So now we've got one more one more 4-bar linkage before we like create our own 4-bar linkage setups and then make a project out of it. And this is just to give you some appreciation of like how easy it is once you set it up as a computer problem. Like, well, you can solve for all of these states with like a millisecond worth of computational work. Then we'll take a look at the vector laws again to see if they still apply. All right, so we've got point O. That's at 0, 0 again. There's O. RA, we go 0 along the x-axis, but up 1/4. So what's theta 1 if we go 0 along the x, but up by L1? What is that value of theta 1? 90, right? Because it's along the y-axis, so its cosine is always going to be 0. Cool. And then RC, I'm going to put in RC next. Go over 1 and down by 1/2. So over 1, down by 1/2. Like that. And now point B is almost 1, like basically 1 over. and then up by 1/2. So over 1, up by 1/2, so somewhere like up here. And then theta 3, something like that. That's what so this is what it looks like. We have same kind of setup that theta 1 dot is 10 radians per second. So that one's going to be a constant, like it's rotating, crank arm is rotating that way. And let's draw in our vectors again. Actually, let's use a different one for that. We'll go blue. So we changed like how this thing is mounted. We took the same bars but just like moved where point C was. What does that do to our vector equations? What happens now, like for constraint equations?
What do you think for the vector ones that we used in the first part, in that first half?
Does it change this?
Yeah, does it change it?
What do you mean, like what vector?
We said RBA plus RA equals RBC plus RC.
Oh yeah, okay, so.
Yeah. Do we need new ones?
Well, for B it doesn't change.
B doesn't change, okay.
RBC, RBA is the same.
Yeah.
It's just different distances.
Yep. Do we need like new equations to solve for them? Yeah.
So this is kind of where we started, right? When I changed the location of C, did I change how these vectors add up? Yeah? There's a different y component, but so like if I write out the two, like the x and the y, oh, that's our dx. So it changed like where point C is, but and the angles are different, right? But it's not. We're still using the same equation. Like it's still same thing. Because those, like when we have three moving parts that are both mounted, like fixed in two locations, it has to be true. Like that vector loop has to add up, no matter how you walk forward or backward along it. So then what happens to this equation? Is it any different? Like is VC, what's the velocity of point C now? I change where it is. Did I change how fast it's moving? Independent of where it's placed. So my question is, like the position of C is describing hinge C. What is this? How fast is hinge C moving? No. Oh yeah. Okay. It's Monday morning. How fast? Yeah, derivative of the position. Yeah. So what is that? What's derivative? What is it? Acceleration. It is, so velocity is equal to acceleration here, just by chance. Yeah, so we could say drc dt is vc. But where's vc? Where's that hinge C going? Is it going anywhere? No?
So would it be 0 at the hinge of the moment?
Yeah, so it's like stuff is rotating around it, but it's not going anywhere because I said that the whole thing is mounted at C. That it can't move in this case. So the fact that I changed like locations, it's not even changing like the system of equations that we ended up with last time, because the position of C, it changes angles like sines and cosines, but it's not changing like how the speeds are related to each other. Yeah. Yeah, yep. And it's the same equations that we just solved in the last one. Like we didn't actually do anything new. It's just we've already seen this. So we can take the same values in there. Cool. Where are we at now? What would be your next step, I guess? That's what I'll check in and see.
Seems like it's a slow Monday morning. It got cold again. It froze. Okay. Yep. Yeah.
I guess, well,
Okay. Yep. Yeah. Plugging the sign. What's your next step? Yeah. Yeah, okay. And then plug them in, we can solve the system. Yeah, yeah. All the equations yeah, just plugging in different numbers. Is this one gonna be easier or harder than the last one? You think harder? Yeah. Oh, tired. Yeah.
Outside. Personally, yeah. So it's the motion, it's the method making like their own right triangles, and then like from there, trying to see like what the
Yeah. Great to do it.
and dx is referring to the distance between a and c.
Yeah.
dy,
And then dy is like how.
so that's a first one.
Yeah. Yeah, then we have
So our first order was failure. Did not do anything. It just fizzled out. Was it the way that was the first one.
I just went and found like the sign for cosine.
Yeah.
Just like
Okay. Yeah.
and I don't remember.
Yeah.
And then you just plug it in something.
Now get you like 40. But sometimes like you feel like I don't really appreciate that.
All right, cool. So big picture is kind of like we know positions. So if we know positions, we know angles, and we know like sines and cosines of angles, right? So we should be able to plug in values for cosine theta, plug in values for sine theta, and all those become just like coefficients in this equation that we're trying to solve. So the only thing this guy. Only things that should be left by time I plug in like known values are theta 2 dot and theta 3 dot. And we figured out that theta 1 was 90 degrees just based on where A is. So what's sine of 90? 1. All right, so that one becomes 1. That's nice. What's cosine 90? 0. That one's nice. Love when things are 0. And then theta 2, we'll get to that in a second. But what about theta 3? What was that? So point, when I go from O to A, that's describing that L1 cosine theta 1, L1 sine theta 1. I went up by 0.25 and left and right 0. So my cosine has to be 0, but my sine has to be 1. What about for BC? That relative B with respect to C. What is that? Triangle. Trying to figure out like sine and cosine of theta 3. Do we know? I saw some people kind of working on it. What did you come up with? Doing like relative, just taking relative position description. Roughly we have like 0.5 plus 0.5 in the J direction. What kind of triangle does that one look like? Pretty close, right? Like within round off error. Yeah, I don't know. It's a little off, but it's pretty close to just like a 90-degree triangle. Because we have our J component is 1 within 0.01%, which is the length of our link. So L1 over L1. We can say that that one is 1. And this one is pretty close to 0. You can plug in the real value if you want, but I don't know. I do love plugging in 0 whenever I can. And then we have that sine theta, cosine theta, but the theta 2 stuff. So this one's a little nicer, right? Zeros. Do we know anything about theta 2 dot at this point? Even without solving for cosine theta 2? Some gut feeling. Yeah. It's got to be 0, right? Because cosine theta 2 is not 0 right now. We know that it's not 0. L2, I mean, it could have been 0, but that would have been weird. So that one's not 0. The only thing that has to be 0 is theta 2 dot. Nice. A little easier to solve this system, right? So many zeros. Zeros are great. It makes everything so much easier. Or you could say approximately 0, like if you're worried about the round off error. But what does that tell you about theta 1 dot, theta 3 dot? Yep. 10. Yeah, that one's 10. Is theta 3 dot going to be bigger than or smaller than theta 1 dot? Is it going to be moving faster or slower than our crank arm? Yeah.
L1 and L3 are the same, right? Or equal?
They're different. Yeah. Good question. If they were the same, that would be.
Yeah.
Yeah. Yeah. Theta 3 dot is smaller?
Yeah, because L1 is small.
Because L1 is smaller?
So it's like a trade-off.
Yeah.
Factor 1/4.
1/4, yeah. So theta 3 is moving 1/4 of theta 1 dot, at least 1/4 speed. Nice when things are kind of lined up like this. And we could go through the same process of like, okay, set up the system of equations and like, okay, now solve for me. But we have a lot of zero coefficients, so it's a little easier to kind of solve for one, then plug it into the other. Same process though. Oh wait, sorry. Like 2.5 radians per second, something like that. Looking good. All set. The next time we'll come work on, I know we've been doing this for a few days now, but there was more to Module 2 than just 4-bar linkages. So next time we'll talk about what we want to do for Quiz 2, build that one. Thanks. Two?